so long to this time. Okay, we should good on the YouTube side. Let's start the seminar.
Okay, great. So hello, everyone. Welcome back to our CFSM seminar series. So today it is our great pleasure to have Dr. Jess Alt as our speaker and talk about his work on vortex breakdown and the time-varying strategies for particle motions in confined geometries. So Dr. Jess Alt received his bachelor and master from Purdue University in 2012. And his PhD from Princeton University in 2017 under the advising of Professor Howard Stone. So he spent 2 years at the Oak Ridge National Lab as Alvin Weinberg Distinguished Fellow in the Computational Science and Engineering Division before joining the Fluids and Thermal Science group in the School of Engineering at Brown University in 2019. So Jess' research interests are at the intersection of applied mathematics, high-performance computing, and the coupled fluid particle solute transport phenomena. So his research interest has emphasized the manipulation of such coupled transport dynamics to manipulate suspended colloidal particle and biomaterials. So with that, let's welcome our today's speaker to start his presentation. So Jess, please feel free to start when you are ready.
Yeah, thank you for the introduction, and just double checking, everyone can see my screen and the sound is okay? Yes? All right, sounds good. Yeah, so thanks for the introduction. I'm Jesse Alt. I'm currently in my 3rd to 4th year as assistant professor at Brown University, which sounds, actually now that I say it, it's been a while, but I still feel like I'm just still learning what I'm doing. So in any case, if you've seen any of my seminars in the last few months, some of these results will be familiar, but some of it will be some progress we've made in the last few months. So I want to talk about kind of just 2 main different projects that are very near the publication stage that we made some progress on. So they're going to be a little bit disconnected in that sense, but they both involve particle dynamics in confined systems. So just as a quick overview of our group's work, we kind of break down what we're working on into these 3 different areas. One is these non-equilibrium coupled transport problems involving both particle, solute, and fluid dynamics, and typically involving electrokinetics, where we have something like a charged colloidal suspension, and interacting with those particles, we introduce some ions into the channel somehow, and those can drive different phoretic effects to manipulate particle motions in confined systems. So this will be the second part of the talk today. The other major area of our group's research is kind of high performance computing in general, especially for coupled multiphysics problems. So this is something that I especially worked on at the National Lab, because at Oak Ridge, they have some of the largest supercomputers in the world. And so at least it's cool to be able to say that you worked on one of the largest supercomputers in the world at the time. I think they're bigger now, but so we look at a variety of coupled transport problems. And then kind of more broadly, just we've worked on a variety of different problems in the kind of fundamental fluids and soft matter research space, especially, which I'll talk about in a second, this vortex breakdown phenomenon, different effects, different problems like, for example, the measurements of hygroscopic fluids in a rheometer, and then also looking at imbibition of oils into dry aqueous films. So this is just kind of a broad intro to what our group is working on. So today I'm going to talk about these 2 projects, vortex breakdown, in particular in a shear-driven cavity flow, and some time-varying strategies to maximize particle motions in what we call a dead-end pore geometry. Again, kind of the motivation for this type of work is varied. You can consider what types of systems have have particle dynamics in fluid in confined geometries. You can think about something like a hydraulic fracturing system where you have all these tiny fractures and it's difficult to drive flow into such tightly confined spaces. Oftentimes they want to inject what are called propant particles into those fractures. As far as I understand, is to prevent the cracks from completely collapsing so that the oil can actually escape. But you can ask the question, how can you actually inject particles into confined systems when it's difficult to drive any flow in such a system? For example, if the scale is very small, the Reynolds number is very small. On the other hand, you can think about advanced manufacturing type systems where, for example, you might want to drive a flow with some type of cross flow or field flow fractionation type device, where by applying some external field, you can separate particles on the fly. This might be useful for like 3D printing applications, where, for example, if you have a collection of quantum dots that you're trying to 3D print in order to make LEDs or something, maybe you want to very specifically select one certain size of particles in order to get a specific color of LED. Well, then it's useful to have techniques to isolate or select or separate different particles by whatever properties they have, size or charge. And so that's something that you could do in kind of a microfluidics type device. On the other hand, you can think about drug delivery applications. Again, you have a variety of confined systems in your body where you want to somehow transport drug molecules. And then finally, biomedical devices, you may want to isolate certain biomolecules or separate or detect or concentrate. And these are all applications where we often want to build some kind of lab on a chip device in order to achieve some kind of manipulation of biomolecules. So these are kind of the broad applications of our group's research. So the first project I want to talk about is a very basic geometry, not at a very high Reynolds number. This is just the shear-driven flow in a cavity. So specifically, we're looking at the flow inside this cavity. It just so happens to be driven by an external shear flow with this external channel flow. And what we'll find is that you can have these closed recirculation zones forming inside the cavity, which very much resemble vortex breakdown, which we'll introduce, and can have a lot of consequences on capture and trapping of particles, or when you get into the other end of the space where you're trying to, for example, flush or clean a system, these effects can hinder or drastically increase the timescale required for cleaning a system. So this is the first project that I'll talk about. The second project, again, we're going to be talking about particle transport in what we call a dead-end pore geometry, and how can we use different time-varying strategies to maximize either particle injection or withdrawal from those confined systems. So this is an extension of a lot of recent papers where every existing paper to date has basically used one boundary condition. We're saying, how can we change the boundary condition as a function of time in order to optimize these types of processes? So this is the two projects that I'm going to talk about today. Just as a brief outline for this first problem, shear-driven flow in a cavity and the vortex breakdown that results from that. We'll talk about just a brief intro to vortex breakdown, some previous observations that we had which motivated this work, which were in a branching junction flow. This goes all the way back to my grad school work. Specifically, we'll talk about the shear-driven flow past the cavity, which is a very popular problem in 2D literature and research, and it has surprising 3D effects when you consider finally the wall effects in a 3D system. We'll talk about experimental observations, numerical simulations, and then some interesting consequences of asymmetry that we've observed, which tell us a little bit about the sensitivity of the flow to geometrical imperfections, let's say, in the experiments. And then for the second project, these time-varying strategies to enhance diffusiophoresis, we'll just do a quick overview of this problem, which has been the subject of probably 5 to 10 different papers. But again, we're going to look at it with a little twist, just changing one boundary condition that previously has just been a constant. We'll define the efficiency of particle extraction or injection, which is something that hasn't been looked at before. And then we'll talk about some strategies to maximize these transports. In particular, can we use pulsed diffusiophoresis, where we repeatedly switch the concentration boundary condition next to the pore, or can we use some kind of time varying condition, like an exponentially decaying solute condition at the wall, or some other generic boundary condition? And how can we do something kind of like reverse function optimization to maximize what we're trying to achieve, which is injecting or withdrawing particles from some confined system. So first, I'll talk about this vortex breakdown problem. And we can start with just a quick introduction to vortex breakdown. It's kind of an old classic problem in the fluid dynamics literature. And the kind of stereotypical example of this is this flow in a cylindrical pipe. So this system has flow from left to right, and they're injecting dye along the center of the channel. And you can see that the first half of the channel is spinning and the second half is stationary. So the idea is the flow should be axisymmetric, but there's some kind of source of swirl, which is the rotation that the flow gets from the moving boundary condition. And you can see what happens above a certain swirl number. So they're actually increasing the rotation speed of the upward channel, the left half of the channel. So they're increasing that rotation rate. That increases the relative balance of the swirl velocity to the axial velocity component. So that ratio, the azimuthal velocity to the axial velocity, is increasing as they keep swirling this faster and faster. And you can see that you end up with this kind of structure that looks a bit like a bubble. And right now they're going to slow down the channel. And then once that happens, everything will be flushed downstream. But the idea is you end up with some kind of bubble type shape here. So that's why it's often called a bubble, a vortex breakdown bubble, where flow just recirculates indefinitely. If you take a cross section anywhere, the net mass flux has to be the same, just because of conservation of mass. You're injecting a certain amount of flow from the left. So what happens, near the center plane is the flow has to increase speed on the outer rim of the pipe, because inside this bubble region, the flow is actually upstream in its direction. And so if you were able to visualize the velocity here using PIV or something, you would actually see that there are two stagnation points inside the flow where the velocity goes to zero. So on this half of the vortex core, the flow is down in the downstream direction, where it then reaches a stagnation point and diverges along this surface over to this other stagnation point, where the flow then goes upstream within this bubble region. And so this will actually recirculate indefinitely. So that's kind of the classical picture of vortex breakdown. If you want a definition of vortex breakdown, you could say that it's an abrupt change in the vortex structure where you have retardation along the vortex core. The flow decelerates along the vortex core and to a stagnation point, and then suddenly diverges. So the stream surfaces diverge. This was actually first observed in the trailing vortices over swept wings in the 1950s. This is a delta wing at a steep angle of attack, where they're injecting smoke where the wingtip vortices are generated. You can see that they maintain this kind of smooth column vortex down to some certain region, where then suddenly the vortex diverges. And it can also be observed in modern flight conditions. Here you have a jet that's suddenly accelerating and moving upwards. And you can see a similar thing happening with this vortex that's generated, visualized with smoke again. Suddenly the flow is actually decelerating along this vortex down to some point here, and then it suddenly diverges and becomes very unstable. So typically this vortex breakdown is characterized by a uniform vortex core, which is followed by a sudden divergence in the stream surfaces. And again, like I mentioned in the video that I showed, it's the ratio of swirl to axial velocity, which is a key control parameter for this. There's been different types of vortex breakdown identified. So these are just three kind of typical ones. They're called spiral type, axisymmetric bubble type, and double helix type. Again, which type you actually get in practice depends on a lot of things, in particular the geometry of the system. So if the flow is expanding, if the channel is expanding or contracting, if it's unbounded, these can all affect which type of breakdown you actually get. And typically there's been a bit of controversy about the interpretations or how to explain or mathematically show whether vortex breakdown will happen. But the basic ideas are that, so these are various interpretations. That the first is that it's analogous to a 2D boundary layer separation. Another is that it's a consequence of hydrodynamic stability. And then this is kind of the more popular interpretation recently, especially it seems to match calculations pretty well. I'll show an example of that later on, but the idea is that the breakdown depends on the existence of a critical state. And in that sense, it's analogous to a hydraulic jump problem where you transition between sub or supercritical states. So you've probably all seen a picture like this. If you're not familiar with the hydraulic jump problem, if you just hold a plate under the sink, then you can see this thin, fast outward flow followed by this sudden increase in thickness of the fluid layer. And so this represents a transition between sub and supercritical states pertaining to a hydraulic jump. But the idea is you can interpret the vortex breakdown in a similar way using similar mathematics. So again, the motivation for the problem that I'm going to show comes from back in my graduate student days, where we were looking at the flow in branching junctions. And what we saw then was, for example, here we have flow entering through the top, splitting. It should be symmetric, except that the experimental quality is a little bad. As you can see, the channel is kind of rough. But the idea is here we have a channel filled with dye, and we try to flush it with clean water. And what happens is you can see that there are clearly these two internal regions where dye just remains trapped. So it just remains trapped and recirculating, and eventually it will diffuse out of the channel. But that's happening on a different time scale from what you would expect. You'd expect all the dye would be flushed out somehow on the convective time scale of the problem, but now you have a diffusion time based on the size of the structure. How fast will the dye diffuse out of this region? So the flushing becomes diffusion dominated once these vortex breakdown regions appear. And then when you introduce something like bubbles or low density particles, you can also see them accumulate rapidly into these regions, and they'll actually remain trapped here internally, just recirculating as long as you maintain the flow. If you actually increase the flow, trying to flush them out with faster flow, it actually just strengthens the trapping. So you need to reduce the Reynolds number below the point where the vortex breakdown occurs in order to actually flush the system. So this can, like I said, prevent systems from flushing properly. It changes the time scale that you would expect for cleaning a system. It can also result in high local particle or gas concentrations, and it can result in asymmetric or unsteady pulsatile flow. And you can use this as a method to capture particles of interest. So this is the motivation for the problem I'm going to look at, because you have here, what you have is a very basic flow geometry, just a branching junction, and which is obviously ubiquitous across microfluidics, all kinds of piping systems, chemical reactors. And what we have is a trapping mechanism that has previously not been identified. And so it begs the question of, are there other very basic ubiquitous geometries which somehow have a source of swirl that can exhibit these vortex breakdown effects also? And so this led us to look into other geometries. So this is just back from those previous results. What I did was look at varying the geometry and Reynolds number to try to figure out some kind of capture regime. And then we showed that this matched the simulation results for when vortex breakdown occurs. So again, this is just motivation for this shear-driven flow past the cavity problem. So the reason we looked at this is essentially, it's a very basic geometry. It's been widely studied in the 2D literature. When you introduce 3D effects, you know that you have some source of swirl inside the cavity, and maybe you also have an axial component of flow along the vortex core in 3D. In 2D, obviously you don't. And so that begs the question, can there be a regime where this swirl number, which is an important criteria for the onset of vortex breakdown, is there a swirl number in these cavity flow problems that can trigger the onset of vortex breakdown? So this is what we wanted to look into. And again, like I said, this problem has been studied quite a lot in the 2D system. In particular, recently, in the SLIPS research, I can't even remember what it stands for, but they were looking at superhydrophobic liquid-infused surfaces, pattern surfaces, where they basically would pattern a surface, fill the patterns or the cavities with some type of other liquid like oil, and then you can effectively get something like a slip length near the surface. And so rather than having a strict no slip condition at the surface, you can have an effective slip condition at the surface, and that can affect overall drag on surfaces. In particular, this was studied more in the context of, turbulent drag reduction, but a lot of the theory in the 2D problems came down to, low Reynolds number problems, especially when you have these tiny confined patterns in the surface. So that's one area where these types of shear-driven flow past the cavity came up recently in the literature. Oh, here is what it stands for: slippery, liquid-infused, porous surfaces. And so the question we're asking is, are there, in the case of 3D flow, any closed recirculating streamlines, in particular, that resemble the vortex breakdown dynamics? So we did find one piece of evidence that this is the case, in particular, this conference paper, Numerical Simulations of Flow in a 3D Cavity Channel from Torchinsky and O'Hearn. And essentially, they were looking at this flow with a symmetry boundary condition at the center, and they did, I'll call them crude, but for the time, computational power was expensive. And so you can see the grid here. It's relatively coarse, but they were able to see these two effects. So here on the bottom, these are two different Reynolds numbers. You can see something like a streamline spiraling down on the center. So this is the center plane. There's a symmetry condition. And then the streamline diverges out of the channel. And then at a larger Reynolds number, they saw something looking like a recirculation pocket. And they gave this kind of qualitative diagram describing what they thought was happening. And so at a lower Reynolds number, you just see flow spiral down to a stagnation point and then diverge out of the channel. And at a higher Reynolds number, they see the formation of this kind of recirculation bubble. And so we wanted to look into this with a lot more detail and see the different types of dynamics, the different modes and transitions that can occur. So this is, again, our system. This is a typical experiment. We're looking from the bottom, and the primary things we're going to vary in this are the width and the Reynolds number. And so here we have a channel filled with dye, and you can see when we run the flow, it will flush the dye and leave behind some dye trapped in this little bubble pocket region. And you can kind of see there is a recirculation happening. It's almost like two toruses that are swirling around. And this dye will remain trapped until it diffuses out of the trapping region. So this is a typical time series just from our experiments, and then compared with a streamlined visualization from our numerical simulations. So this is kind of a collection of 3 different experiments. Oh, no, sorry. Here we're varying the Reynolds number with time. So as you move top to bottom, time increases. So what you would expect here, for example, at low Reynolds numbers, you have dye originally in the cavity, and as time increases, you expect it to be flushed out, which is really what we're seeing here. But the interesting thing is, as you increase Reynolds number, you start to see some dye remaining over longer and longer timescales. And then especially at the highest Reynolds number, you see these very strong regions where dye is just captured. So it's no longer being flushed out, it's actually diffusing out. So if you continue this on for a very long time, they'll still disappear. But the idea is increasing Reynolds number sees some kind of transition from where the flow is just flushed out to where it has to diffuse out, which is a much slower process. So there's an apparent transition as the Reynolds number increases, and above this critical Reynolds number, the dye remains trapped for a much longer time scale, and then flushing the system in this case becomes diffusion limited. So just looking at a variety of different Reynolds numbers and cavity widths, it's not really important what the specific parameters are here, but the idea is this is kind of a variety of the results that we observed experimentally. You can see there's kind of a collection of different behaviors that you can observe, including either single or multiple trapping regions. A lot of times there's a void in between the two regions, and you can also see symmetric, for example, in D, or asymmetric as in B. And in some cases, this trapping region can basically occupy nearly the entire cavity. So obviously it's important to know. So, well, the interesting thing is in 2D, you expect that the cavity is a trapping region because you just have these recirculation zones, which obviously have to be closed streamlines. But in 3D, it's not obvious. And indeed, at low Reynolds numbers, it's definitely not the case. It requires inertia to trap flow in the cavity, which is what we expect from vortex breakdown. So looking at some of the numerical simulations we've done, first, just as a sanity check, we reproduced the results of Torchinsky and O'Hearn. These are we redrew their schematics and simulated the flow at the same Reynolds numbers. You can see that we do get similar effects. The interesting thing here is on the left at the low Reynolds number, flow spirals down to this center plane stagnation point. Once you reach above this, whatever the critical transition is, these outer stagnation points actually emerge from the center plane along with this orbit. And this orbit is actually stable on the center plane. So flow on the outer, coming from the inlet, spirals down to this orbit. And from the inside of the stagnation point, it actually spirals outwards to that orbit. And then it's unstable on the stream surface of the bubble. So it diverges off the center plane to these outer stagnation points. So in any case, this is a good sanity check that our simulations kind of match this one observation from the past. So we did quite a few simulations of varying the cavity width and Reynolds number. And actually, the dynamics are surprisingly complicated. This is a phase diagram showing all the different types of trapping modes that we observed. So these are kind of just names that we came up with based on what they kind of look like. And I'll try to visualize some of these transitions that are happening. So each of these solid lines is a critical Reynolds number for transition between modes. So first we can take a look at, for example, this red dashed line. Essentially, we're holding Reynolds number constant and increasing the cavity width. And what we'll see is a transition from a single bubble breakdown to a double bubble breakdown. And you can see that here. So here we're increasing the cavity width. And you can see originally you have this single recirculation zone. As you increase the cavity width, it becomes multiple regions, 2 regions, which are symmetric. And as you increase much further, you don't approach the 2D limit because you still have walls, even if the width is very large. So near the walls, you have something that becomes independent of the width, right? These structures, if you were to rescale these based on L instead of D or D instead of L, then these would actually start to look identical. So it loses the influence of the other wall. So regardless how wide you make the cavity, you'll always have these vortex breakdown bubbles near the side walls. Near the center, it's going to look like the 2D flow, obviously. So in this case, the cavity width is increasing from 0.75 to 15, and we're holding Reynolds number constant. And then obviously, as the width goes to infinity, the vortex breakdown near the side walls becomes independent of cavity width. And that's something you can see as you increase the cavity width, this outer transition levels off and the critical Reynolds number becomes independent of the width, which is what you'd expect. So next we can take a look at this other transition, this blue line, where we appear to go from this diverging single stagnation point, so that's not a vortex breakdown case, to the blue, which is double bubble breakdown, to the orange, which is single bubble breakdown. So the way this works is, here we're holding the cavity width constant and we're increasing Reynolds number. So originally at low Reynolds numbers, this is kind of the typical picture where you just have a single stagnation point on the center plane. You don't have any trapping or anything. And as you increase Reynolds number, suddenly these two regions appear off center plane and they're well separated. And then as you increase the Reynolds number, they'll actually grow and eventually merge. So here the cavity width is 4 and the Reynolds number increases from about 80 to 150. And so it's going through two transitions at approximately Reynolds number 84 and 105, where these regions first appear out of nowhere and then they merge at a higher Reynolds number. So it's always a little bit contentious whenever you claim something is vortex breakdown, just because kind of the interpretation itself, it remains a little contentious. And so what we wanted to do is do a little bit of analysis to confirm this is vortex breakdown. And so, for example, here is half of the channel for one of these cases where there's two separated bubbles. So this is symmetric about the center plane. There's another bubble over here. And we're just looking at the magnitude of velocity along the vortex core. So we have one streamline plotted through the vortex core and then another streamline visualizing this bubble. And the color here is the magnitude of velocity. So you can see, obviously, there's blue regions here that represent essentially stagnation zones. It's not obvious if the velocity is 0 there. But then in the lower plot, what we're plotting is magnitude of velocity along the vortex core. And you can see as a function of Reynolds number. So you can see in the Reynolds number 90, that's the upper line, the darker blue, there is a slight decrease in velocity in this region. And then as you increase Reynolds number, it becomes a stronger stagnation region. Essentially, the velocity decreases, which is moving downwards, but it also separates into these two separate peaks. And then finally around, let's say, Reynolds number 98, these go extremely small and become essentially stagnation points. And then they continue to separate as Reynolds number increases. So this bubble region is basically appearing out of nowhere and growing as the Reynolds number goes beyond that critical transition. So again, as the Reynolds number increases, you have two stagnation points which just suddenly appear at some qualitative dynamical transition point, and then these bound to the recirculation region, which will then grow with Reynolds number. So I mentioned previously this idea of criticality, which was an interpretation proposed by Benjamin, and he was analyzing axisymmetric swirling flow. And he proposed that the vortex breakdown depends on the existence of a critical state, like in the hydraulic jump problem. And so you can actually determine this criticality from a velocity field. You have to know the velocity field in advance. So this still requires, analytical solutions or CFD, in our case, CFD. But you can determine criticality by solving this ODE. So this is, here you have UZ, that's the axial velocity component, and U theta, that's the swirl velocity component, and phi c is some function we're trying to solve. So again, this is strictly valid for axisymmetric flow, because that's what this interpretation was made for. So in our case, clearly we don't have perfectly axisymmetric flow. So we have to use some kind of procedure to axisymmetrize about the vortex core, which is a little bit complicated because the vortex core is also not a straight line. And so there is a bit of approximation in here in our numerical methods to when we apply this method. But the idea is this is subject to these boundary conditions for phi. And the idea is if the solution has a root within whatever radius you're inspecting. So in the case of Benjamin, he was looking at just a pipe flow. So he had a clear radius. For us, we were essentially making a cylinder about the vortex core. So we have to pick an outer radius for that cylinder within which we're going to analyze the flow. Because of, if you keep increasing the cylinder, then it will leave the geometry, or it might cut one of the corners of the cavity. And so again, there's a bit of hand waviness going on. But if you do this for our double bubble breakdown mode, again, you have symmetry about z is 0. Then at a lower Reynolds number, you get here, our crit is the location of the root of this solution to this equation. So again, remember back to the definition, if the solution has a root within your radius of analysis, then the region is subcritical. And so again, you have to pick an outer radius to compare to, but the idea is at a lower Reynolds number, you don't see any roots in this outer region. And then as you increase Reynolds number, you start to see the appearance of roots to the solution of this ODE in exactly the same location as what we say is a vortex breakdown region. So it appears, although again, like I mentioned, there's hand waviness going on, it appears that this interpretation is valid for our data also. So I think that gives some credibility to us calling this vortex breakdown, and also some credibility to, again, the interpretation of subcritical versus supercritical breakdown. So at narrow cavity widths, the flow gets even more complicated. And there are actually 5 different modes that we've identified. And you can see those here. We're calling these at type A, that's the purple, this converging single stagnation point mode. So here the flow actually comes down to the center plane stagnation point, then spirals outwards, then flows towards the outlet. In the green region, we have what we're calling this corner vortex trapping, which is a little bit unique because the stability and the sense of orientation is opposite from the typical vortex breakdown you observe. Then increasing Reynolds number further, you get into the gray region. That's the diverging single stagnation point mode, then single bubble breakdown, and then finally what we'll call fully reversed flow, which is essentially where the single bubble region gets so large, it encompasses the entire cavity, and those outer limiting stagnation points end up on the cavity walls. So we'll just call that fully reversed flow, which is essentially where it's just dominated the entire cavity. So this corner vortex trapping, again, I mentioned, it's a little bit funny. So here, these are 3 different Reynolds numbers, all at the same width, which is relatively small. And here the Reynolds number is 30 over here, just visualizing this trapping region. And then here for B and C, it's 20 and 40, which notice is pretty small in the context of vortex breakdown. Remember, this was originally observed at high Reynolds number flows, external flows, like wings at high angle of attack at high Reynolds number. And so here, this mode appears to be different from the typical vortex breakdown bubble. In particular, like I said, the stability is opposite. So it's stable on the vortex core, the outer stagnation points. So here and here, these stagnation points are stable on the vortex core, which means flow is towards them on the vortex core, both outside and inside. And it's unstable in the shell of the vortex. So that's opposite to what is typically seen in vortex breakdown. So we're a little bit confused by that. We have yet to apply this criticality condition to this case, but we'll probably work on that in the next few weeks. And the interesting thing here is this mode can exist even with very low inertia, even around Reynolds number of order 1, which, like I said, is a bit curious because the vortex breakdown itself is an inertial effect. And so it's pretty rare. I don't know of any case where you can have vortex breakdown at order 1 Reynolds number. And so this is something that we're trying to understand a little more also. Finally, this idea of asymmetry, like I mentioned in the experimental results, we have some observations where the flow is clearly asymmetric. And so we're wondering, is the solution itself, is the symmetric solution unstable or something? Is there some kind of symmetry breaking going on? Or is this just an issue with the experiments where it's the flow, there's some kind of minor asymmetry in the experimental setup, and the flow happens to be quite sensitive to those symmetries. So we wanted to test the sensitivity of the flow in the cavity to this asymmetry in the outer channel flow. So essentially, we just perturbed the fully developed velocity inlet condition by some kind of linear function with a small asymmetry perturbation. And so what you find is, as you increase the magnitude of that asymmetry, here it's 0.01, 1%, 10%, or 20%, you actually can see some kind of distortion in the shape of these vortex breakdown regions. And so even with this 1% asymmetry, it actually appears like the lower half of this trapping region may no longer be a closed recirculation zone. So if you were actually to flush dye out of this system, it's not really obvious from these pictures whether dye will even remain trapped here or not, because it appears that those streamlines may not be closed recirculation loops anymore. So in that case, the flow does appear to be pretty sensitive to asymmetry, especially if you think about like the trapping capacity, which is, I guess, the volume of the total vortex breakdown regions. And so relatively small asymmetries may affect the trapping quite a bit. So what we did was we simulated the advection diffusion of a concentration field with our asymmetric flow fields to try to reproduce the experimental observations. And you can see that these actually match the experiments pretty well. So this is just an advection diffusion solution of some kind of concentration field, some tracer field, and we're just visualizing certain contours. And so it does seem like there's just some minor asymmetry in the experiments, even 1% asymmetry, which is resulting in these biased breakdown dye trapping regions. So finally, if you can compare the experimental results with the numerical results. These are a bit difficult to compare because, again, when you get near these transition points, it's not obvious if there's actually dye being trapped or not. And so you have to use some kind of visual criteria. Is the velocity, or is it just a stagnation zone where the velocity is slow? And so convection is very slow to drain the fluid out, drain the dye out, or is it actually a trapping, in which case the dye still leaves very slow due to diffusion? It's a bit difficult to identify those transitions. And so there's a lot of transitional cases from our kind of visual observations, but in general, you get a pretty good match between experiments and simulations. Okay, so I took most of my time on that problem, so I'll rush through this problem. So again, we're interested in time varying strategies to enhance diffusiophoresis in a pore. So just very quickly, again, we're interested in moving particles in confined geometries without flow, using some kind of other strategy. So the idea is, what control mechanisms do we have to control particle motion in such systems, and what is the efficiency, and how can we increase the efficiency? So this is kind of the canonical problem, which Professor Shin worked on a lot. There's probably 5 to 10 papers looking at this problem, but it's, for example, how can we speed up particle transport in a pore? If you flow a solution of particles past a pore, they will eventually diffuse into the pore to fill it just from Brownian motion, but it's extremely slow. So for example, 1 micron particles in a 100 micron pore, it's going to take 5 hours using diffusion to fill the pore. So we can use this other effect called diffusiophoresis, which is an effect whereby charged particles spontaneously move either up or down a salt concentration gradient. So the velocity is proportional to the gradient in the log of the salt concentration. If you just put salt in a flow solution containing particles, those particles will move either towards high or low salt concentration. That's called diffusiophoresis. So you can imagine an experiment where you fill a channel with salt, you flush a channel, you flush a second solution containing particles past the pore, and what will happen is that salt will diffuse out of the pore and pulling particles in a much faster time scale. It's much faster because this is related to the diffusion of the salt rather than the diffusion of the particles. And so those have, possibly 1,000 times higher diffusivity. And so you can have 1,000 times increase in the speed of dragging particles in or out of a confined system using these effects. So the typical experiment, this was done by Professor Sang-Woo Shin, was to introduce a bubble separating your two solutions to essentially get what's a nearly discontinuous initial condition. And so then as soon as this bubble passes the pore, it separates the two solutions. You get this outward diffusion of salt, which pulls particles in. And you can see they get sucked in over a few minutes rather than hours. And if you want to withdraw particles, you can just flip the way you set up the system. You just have to do these particular particles based on their charge and size. Do they move towards high salt concentration or low? It also depends on the choice of salt, whether the cations or anions have higher or lower diffusivity. So what we've done is just think about what's the actual efficiency of this extraction or injection problem. The governing equations here are very basic. It's just we're just considering no fluid motion at all, pure diffusion for the solute. We start with an initial condition that's just uniform. We apply a step boundary condition, that's some value beta, and we have a no flux condition at the other end. That's a very basic diffusion equation. Here, the characteristic length is pore length, and the characteristic time is the diffusion time, L squared over ds. So this has an analytical solution, which can be derived very easily. And so we know the salt concentration distribution in the pore at all times for all locations. For the particle motion, we're assuming purely diffusiophoresis. We're assuming there's no fluid advection, no particle diffusion, which is fine because it's much slower compared to the solute diffusion. And we're ignoring all 2D and 3D effects, such as dispersions and things like this. But there's been a lot of work on this recently. So if you're interested, you should see the works by like Gupta, Chu, Alessio, Kerr, Stone, Shin, Shim, Carr, etc. There's a lot of work on this, especially in the last 5 to 10 years. So the governing equation for an individual particle experienced in diffusiophoresis is just the velocity equals this mobility coefficient, gamma p, times the gradient in the log of the salt concentration. You can just integrate this directly. And for now, assume that this mobility is a constant. It tells you how the particles react to a salt gradient. Again, this ignores finite to bilayer and variable size potential effects. So in this case, the dynamics of a particle in the pore, it's governed by the solute contrast ratio, that's the boundary condition, and its mobility. That's how it reacts to a salt gradient. So you can see, for example, just motivating, what is the efficiency of extraction? Here, these are 3 different cases, increasing the magnitude of the mobility. So on the left, we have a bunch of particles in the channel. The bottom is the number of particles over time. Top is the salt concentration. You can see the salt decreases, the boundary condition is 0.1, the initial condition is 1. So it decreases to 0.1, and roughly half of the particles are pulled out. When you increase mobility, you're able to pull out a lot more particles. And you increase it even more, you can pull out nearly all the particles. So obviously there's a very simple metric for defining efficiency, which is just thinking about how many of the particles were extracted from the channel, if they're initially randomly distributed or uniformly distributed. You could also think about, what fraction of the pore will all particles be removed from? So if you were to place a single particle at this point, and integrate forward in time, it would end up exactly at the pore entrance after the full process is done. So you can do a single integration to calculate the efficiency for a single problem because we know analytically the salt concentration. So our idea is just place a particle at the pore entrance and integrate backwards from large T. You start at, after the process is all the way done, start at large T, place a particle at the pore entrance, integrate backwards in time, and that'll shoot you back to exactly where it started. And that tells you the efficiency of withdrawal. So this is extremely fast to do because everything is known analytically, and the particle integration is just explicit. So we can do this for a huge amount of parameters in order to get this huge parameter space. Otherwise, without an analytical solution, you'd have to do full simulations of the particle and concentration fields, which will take much, much longer. So this strategy allows us to calculate these very quickly. So these are the efficiencies based on the mobility versus the salt contrast ratio. And you can see that for negative mobilities, the efficiencies are actually tend to be higher than for positive mobilities, which this matches what's been seen in some recent literature, especially by Professor Shin. So there's a paper on the laundry cleaning problem. You can take a look at that if you're interested in this difference between negative and positive mobilities. But there are regimes where the efficiency is relatively low. And so it's useful to think about how to increase those efficiencies using some strategy. So the idea is, like, for example, first of all, could you just flip the boundary condition repeatedly using some kind of system like this, using a collection of bubbles to separate the different solutions? You flip from high to low, high to low, high to low. The particles will repeatedly move either, let's say, up or down the concentration gradient. So they'll move out some, they'll move in some, they'll move out some, they'll move in some. Will this actually give you a net effect? It may, because the relationship for diffusiophoresis is nonlinear. So you just have to actually do the calculation. So for example, here is a negative mobility case where we will pulse this by repeatedly switching between 0.1 and 1 concentrations. And you can see with each subsequent pulse, some additional particles are removed. So this kind of tells you the efficiency of extraction is greater than the efficiency of injection. But in this other case, same contrast ratio of a factor of 10, but with a positive mobility, the injection is much stronger than the withdrawal. And so repeating this cycle will just inject the particles even further into the confinement. And so there you need some other strategy, not this strategy, because this will just impact the particles further. So in order to figure out the injection efficiency, you could do exactly the same thing, place a particle at the pore entrance, but now integrate forward in time and see where it ends up in the pore. How far does it actually penetrate into the pore? And so this is what we've done here. If you want to calculate the net effect of this pulsed approach, you have to somehow subtract the withdrawal efficiency, the injection efficiency from the withdrawal efficiency, which is done here. So this is the net efficiency of one cycle of flipping from high to low to high. And you can see in the regions where this is positive, that means that the withdrawal efficiency is greater than the injection efficiency. So you can continue to pulse in order to see more withdrawal. But if this is negative, then this strategy won't work because the particles will just be impacted further and further. And if this is 0, then you can think about one particle starting at the pore entrance. It moves somewhere into the pore, and then after the cycle, it moves exactly back to where it started. So if this is 0, that's the case. You just have particles repeatedly moving to the exact same positions. So another strategy, because here, everything that's been done in previous papers involves a step boundary condition. It's convenient because you can use a bubble to separate the two solutions. You get something like a step boundary condition. But you could just as easily use multiple syringe pumps, for example, to mix different salt concentrations and get whatever time evolving concentration you want at the pore entrance. So you can think about something like, for example, an exponential boundary condition. where you have this constant B now, which you can control. So if B is very large, then this term will disappear very fast, and it's essentially like the step boundary condition. If B is small, then you're basically prolonging the change in concentration at the pore entrance, and in some sense, you may prolong the diffusiophoresis and enhance efficiency in that way. So this problem also has an analytical solution. It's just a little bit different. Again, it's an infinite sum like this. But the idea is you now have a free parameter B that you can use to optimize the efficiency. So this is something that we tried. And indeed, if you look comparing the step boundary condition here versus the exponential boundary condition with a relatively small B value, here you can see that these efficiencies are higher, than over here. And so just by changing from a step boundary condition to an exponential, you can actually improve the withdrawal of particles or oil droplets or whatever from your confined flow system. So the last thing I'll say is there's nothing that limits you to using an exponential or step boundary condition. Essentially what we're trying to do is kind of do this like reverse function optimization. We want to find some function that maximizes this withdrawal or injection efficiency. So this is something that we don't really know too much about. Currently, what we're trying is we made a generic function that's some kind of sum of exponential and sine terms. We have a lot of free parameters here, the number of terms and these coefficients. We're just making some generic function. So this also has an analytical solution. And so we're able to calculate things quickly. But the idea is right now, all we're doing is basically like a Monte Carlo approach, guessing these parameters and calculating the resulting efficiency. So we're looking for a smarter way to do this. So if you have any ideas about reverse function optimization, that would be very helpful. So in any case, I'm sorry I went a little bit long, but I'll end here and I'm happy to take any questions.
Hi, Jess. Yeah, thank you so much for the very interesting talk. So it gives a lot of information, especially for people like me without too much background training in the fluid mechanics. So before I can ask my question, so I would like to give the opportunity to our audience first. Is there any question from our audience?
So can I ask questions?
Yeah.
Yeah, so I have two questions. First, thanks to Jesse for the very interesting talk. I enjoy a lot some new stuff there. So the first, my first question is about the vortex breakdown phenomena. You mentioned that this actually, in addition to the geometry, the only important parameter is the initial weight compared to the viscosity part. So Reynolds number is the only parameter there. So I'm not sure if there's for example, currently you only consider the Newtonian fluid. I'm not sure if you add something, for example, the polymer solution, you can change the viscosity, but you add a little bit of the viscoelastic property in the phenomenon. I'm not sure if this will give you consistent observation, or introduce the viscoelastic will change the phenomenon when you only use the Reynolds number to quantify this phenomenon.
Yeah, that's a really good question. This is actually something that Amy Shen has worked on a little bit in Okinawa, and also Hyungsoo Kim and KAIST. He's been doing a little bit. I'm supposed to help him a little bit with the simulations sometime soon, but it's definitely an interesting question because you do have this, in a sense, it's a stagnation zone, but it's also kind of a high shear zone. And so it's interesting to think about how the non-Newtonian effects could change that. I don't really have too much intuition about that. Yeah, but it's definitely interesting to look into.
Okay, thanks. Then I have another question about when you use the pulsed flow rate control to try to extract the particle in the second part. You extract the particle from the pore, the small channel. I'm not sure because you consider this process is totally reversible. I'm not sure if during the process, do you consider the self-diffusion of the particle?
No, because well, that's also a good question. So in this model, it's very simplified. Essentially, that time scale for particle diffusion is so slow compared to this time scale, because here you have the solute diffusion, which is, let's say, ds is the solute diffusivity. You also have the particle diffusivity, but that ratio is something like 1,000. Well, for a 1 micron particle. I mean, if you get into, nanometer scale particles, you'd have to consider that also, which we don't. Typically, we're dealing with 200 nanometers or larger particles, and so in that case, there's kind of a wide separation in the timescales, so you don't really need to worry about it. The other time you might have to worry about it is if you had weakly charged particles, because we're assuming that this mobility constant is on the same order as the salt diffusivity. But if that's not true, then you probably have to bring in the particle diffusion.
Yeah, my last question is about the when you input the parameters. I'm not sure if you consider the flow property or for the particle is depend on the local concentration, because if you consider you extract the particles through the channel, then the local concentration actually is time varying on each different location. So if it's a constant property to do the simulation, maybe you will get quite different observation if you consider the properties depend on the local concentration of the system.
Yeah, it's a really good point, because the mobility, well, first of all, the zeta potential is a function of concentration, and then also the mobility is a function of concentration and zeta potential, and so concentration through there again. You have to bring in finite Debye layer effects. So we're just taking like the very lowest order model possible and assuming kind of qualitatively, because we're trying to do these optimizations where we have to run many simulations, and so that's something that we will bring in. We're just doing like a kind of the very fast calculations now, just to get our minds around what to do.
Okay.
Yeah.
Thank you, Jesse.
Yeah, thank you.
Yeah, great. So any other question from our audience? So maybe I can continue my question by following up with Zen. So seems for your first part of your talk, so you basically perform the CFD simulation. So for example, when you construct your phase diagram. So I'm just wondering how many like simulations have you performed when you try to construct the phase diagram? So I saw a lot of like a data point, but in order to construct the full diagram, so I'm assuming it might be like a lot of like simulations needs to be done. So may I ask how many data points did you collect for that diagram?
Yeah, too many. So we kind of did like it's possible that we've actually missed transitions, because essentially we're just looking for the critical values. And let me just find that really quick.
Yep.
Yeah, and so essentially we're just identifying, we're not doing simulations at every single value. We're just looking for the transitions. And we did kind of exploratory simulations in these regions. And it's possible we missed, a little pocket where there's another mode. And I don't really know how you could find those unless you did a staggering number of simulations. And so these are, we would start like here at 25, then try 75, and then it looks different. And so we narrow our search.
I see.
Yeah.
Okay.
But it was still a lot.
Yeah, that's a significant amount of work to construct this diagram. So
Yeah.
I always appreciate the phase diagram that our researcher can provide. So that will be nice. And for your second part of the talk, so seems you are trying to plot some kind of particle extracting and injected back to the pore or back to the channel. So did you just follow the analytical formula, like you maybe modify the some kind of parameter in the expression, so you can know basically how many particles or mass can be extracted from the channel? But I do see some particle. I'm not sure if those results come from the analytical solution, or you perform some particle dynamics or something.
Yeah, let me grab that really quick. You're talking about these?
Yes.
Like in the middle here?
Right.
So these are just individually integrated particle trajectories.
Oh, particle.
So essentially we're just integrating this equation for the
Oh.
particle motion using the theoretical salt concentration.
Okay, so this is a particle dynamics simulation result.
Kind of, but they're all independent trajectories.
Mm-hmm.
Yeah.
Yeah, but each particle, the motion of the dynamics of each particle can be governed by this governing equation. So,
yeah.
Okay, so basically we can solve that. Okay, that makes sense. Okay,
Yeah.
So my last question is about your last part of the talk. So you are trying to alter the position of the oil bubble and your maybe salt like a solute. So I'm just wondering, have you ever thought about the external field? You use the external field to alter the concentration of your salt, like a solution in your system, like maybe I'm thinking about the electric field, because the salt solution is more like a charge, like particles, then under like a different electric field. So we can consider either AC or DC to alter the charge distribution inside of the system, so that we can kind of control the concentrations. I'm not sure if you have ever think about that.
So you're saying that you can use an external electric field to somehow control the salt concentration?
Right.
Is that possible?
I'm thinking, I'm not sure, because the charge, the particle gonna to respond to the electric field, because based on my other project.
Sorry to interrupt, but the bulk solution is still mostly charge neutral.
Yes, it's charge neutral. Yeah, but under the electric field, they say the positive charge gonna to
oh, you're talking about the particles?
Yes.
Oh, okay. Yeah, so then you could have so I have never done coupled diffusiophoresis plus external electrophoresis. I know it has been done. There's a paper from a Korean group in the last couple of years that did this in a lab on a chip system. I don't exactly remember. They did see some kind of good efficiency increase. That's an interesting idea. Yeah.
Yeah, because these days I'm just trying to use the electric field to do some like to extract the water from the air, like different like humidity. So I'm trying to see if the water, like a molecule, gonna to respond to the electric field like efficiently, so we can somehow take advantage from there. But yeah, we can discuss that later.
Yeah, thank you.
That's interesting. So with that, I'm not sure if we may have further questions from our audience. So if not, I think we can close our today's discussion. So thanks again to our today's speaker. So give us a very interesting talk, and let's keep in touch. And we will have another like a CFSM seminar next week. So hopefully we're gonna to meet each other later soon. So thank you so much.
Thank you.
Thanks for attending today's
Jesse.
seminar.
Thanks.
Bye.